Think about this. Farming, I mean, it absolutely needs water, right?
Right.
Without it, well, no crops.
Exactly. It's fundamental.
And for ages, we've tried to figure out how to get water where, nature doesn't quite provide enough. That's irrigation, essentially. But it's way more complex than just, say, digging a ditch. There's a real system behind setting up these vital water delivery systems.
Absolutely. And that's what we're diving into today.
Yeah, today on the Deep Dive, we're going to unpack that exact process. We're working from a pretty detailed irrigation survey document.
Right. And our mission, you could say, is to really understand the methodical steps involved in planning and building irrigation for farmland.
Okay.
This survey document, it lays out pretty much everything that goes into making sure water gets to the crops efficiently. It's a fascinatingly detailed process, often overlooked.
Detailed sounds about right. Our source is this comprehensive irrigation survey doc. It outlines the procedures, the crucial factors, even the technical specs involved.
Yep, it's all in there.
Okay, so let's start at the beginning. What exactly is an irrigation survey? What's its main job?
Well, in simple terms, an irrigation survey is the initial investigation you do before any irrigation project can really start.
Right.
The document puts it like this. It's a survey done to bring irrigation facilities to cultivable land. And the big goal,
More food.
yeah, to increase agricultural productivity, it's the absolute foundation. You can't build without it.
So it's the groundwork.
Yes.
Literally.
Okay.
Okay. Now, the survey we have, it mentions different ways to irrigate land briefly. Could you give us a quick rundown of those methods before we focus in?
Sure, yeah. The survey touches on several main techniques. You've got surface irrigation, that's where water flows over the land, mostly by gravity.
Okay.
Then there's localized irrigation, like drip systems. They deliver water right to the plant roots, low pressure, very targeted. You also have sprinkler irrigation using overhead sprinklers. Center pivot is a type of sprinkler system you see in those big flat fields.
Right, those big rotating arms.
Exactly. Then there's sub-irrigation, sometimes called seepage irrigation, where water comes up from below to the root zone. And finally, lift irrigation, that's for moving water uphill, basically, from lower ground to higher ground.
That gives us a good overview. But our source today, it makes it clear we're really zooming in on one specific type, doesn't it?
Absolutely, yeah. This deep dive is specifically focused on surface irrigation. The survey document really dedicates its detailed discussion to this method.
All right, surface irrigation it is. So for this type, what are the main parts, the sort of crucial components you need to think about when setting one up?
Well, the survey points to three major components for surface irrigation. You have the headworks area, the canal alignment, and the command area.
Okay.
Think of it like a chain. The source, the transport route, and the destination for the water.
Okay, let's break down that chain. The headworks area, what's that all about?
Right, the headworks area, or you might hear it called the intake area, that's where the whole system starts. It's the point where you actually take water from the source, could be a river, stream, reservoir, and you divert it into the irrigation canal network.
And the survey even has a picture of this, showing river water being channeled into a canal, right? Helps visualize that start point.
Yeah, exactly. It shows that diversion point clearly.
Okay, next link. The canal alignment. Sounds pretty straightforward, the path the water takes.
Precisely. The canal alignment is the man-made waterway. The canal itself, it's designed to carry the water from the headworks, that intake point we just talked about, all the way to the farms and fields that need it. It's the main transport line.
The artery, you could say.
Yeah, good analogy.
And the final piece.
Yeah.
The command area. What's that referring to?
The command area is the specific geographic zone the system is designed to serve. So specifically, it's the farmland, the place where crops are grown, and where that delivered water is meant to help them grow.
So it's a logical flow, just like that figure shows. Headworks first, then water travels along the canal alignment, and finally reaches the crops in the command area. Makes sense.
A clear sequence.
Now, setting up something like this, it's obviously not a quick job. The survey lays out a general process. What are the key stages involved in doing an irrigation survey?
Yeah, the survey identifies 6 main stages. First is the project selection or identification study. Then comes the pre-feasibility study. After that, the detailed feasibility study. Then detailed design and estimate, followed by the final location survey, and lastly, the final survey report.
Wow, okay. A lot of steps.
It's a very systematic approach, yes.
Let's take that first one, project selection and identification. How does a project like this even get started? Who decides we need one?
Well, the survey mentions 2 main ways. It can come from public demand, local farmers, communities asking for it.
Okay.
Or it can be initiated by the government, where authorities see a need to boost agricultural output in a certain area.
And if it starts with the public asking for it, are there like specific hoops they need to jump through?
Yeah, there are some key conditions mentioned. First, at least 2/3 of the households who would benefit need to sign a request form, so broad support.
Right.
Second, there shouldn't be any existing water rights disputes that could block it. Third, the beneficiaries, the future users, they have to commit to handling the future operation and maintenance.
Okay, so they take ownership.
Exactly. And finally, and this is crucial, there just has to be enough water available at the source to actually meet the irrigation needs.
All sound pretty essential. So once a potential project is flagged, what's the very first investigative step?
It kicks off with what they call a desk study. This means looking at the farmer's request, any other documents about the area, and importantly, locating the proposed project site on maps.
What kind of maps?
Topographic maps showing the land's shape, maybe Google Earth or other satellite imagery, GIS maps. Basically getting an initial feel for the terrain from existing data.
Okay, starts with research. Then what? I guess you have to actually go there.
Absolutely. If the desk study looks promising, next up is a field visit, sometimes called a walkthrough survey or reconnaissance.
Boots on the ground.
Exactly. And the survey lists the kit they'd bring, the request form, questionnaires for locals, maps, of course, notebooks, a GPS device for marking spots, stopwatch, calculator for quick sums, a camera, measuring tape.
Sounds like they're ready for anything.
Pretty much. It's a real hands-on investigation.
So what are they actually looking at during this field visit? Seems like a lot to check.
It is quite comprehensive, yeah. They'd verify the proposed intake location. Is it actually suitable? They measure the water flow there. That's called river gauging.
Yeah.
They'd walk the proposed canal route, marking a tentative path with GPS. They're also looking out for problems like landslide risks or erosion issues. They observe current farming, current water management, if any. A big task is marking out the cultivable command area, the actual farmland that could be irrigated.
Right, the target zone.
Exactly. Then they assess practical things. Market access, how easy is it to get to the site? Are construction materials available nearby? They look at the local community, who benefits. And crucially, they talk to the farmers, gauge their willingness to maybe provide land, maybe contribute to costs.
That's a huge amount of info gathering for one visit. Let's dig into some of that. Choosing the intake area, what are the absolute must-haves there?
Several critical factors the survey highlights. First, the water source's catchment area, the basin, needs to be big enough to supply the water needed, both in wet and dry seasons.
Reliability is key.
Absolutely. They need to think about reservoir size if one's needed, and pick a spot that won't flood valuable land or, say, protected areas. The ground itself needs to be stable.
How do they check that?
They do some investigation, like drilling, soil testing to see how deep the bedrock is. This helps decide what kind of structure to build: a dam, a weir, a barrage. And then practical stuff. Can you get to the site easily? Or can you build a road? Are materials and labor available?
Makes sense. Reliable source, stable ground, feasible construction. You mentioned water gauging earlier. What exactly are they measuring?
Right. Water gauging gives them key data about the source. They measure the current flow rate, the discharge. They calculate the yearly discharge too. They find the highest flood level, HFL, and the lowest water level, LWL.
Highs and lows.
Yep. And they check silt levels, how much sediment is in the water, all vital for knowing if there's enough water long-term and what challenges the system might face.
Okay, so reliable source identified. Now, getting the water to the fields, what goes into deciding the canal alignment, the route?
Choosing the canal route involves balancing several things. The main aim is obviously connecting the intake to the command area efficiently.
Shortest route.
Not necessarily the shortest, but the best engineered. It needs a suitable slope or gradient. Too steep, you get erosion in the canal. Too shallow, sediment builds up, blocking flow.
Ah, okay, a balance.
Exactly. They'd also tentatively plan secondary canals branching off. Critically, the alignment has to allow water to reach all the designated farmland. They try to minimize earthworks cutting and filling to control costs, and they try to avoid valuable land, religious sites, protected zones, national parks if they can.
Makes sense.
Oh, and where it has to cross rivers or roads, they aim for perpendicular crossings if possible. It's generally better structurally.
Minimize disruption, maximize efficiency. Sounds like quite the puzzle. And the last bit of this initial stage, marking the cultivable command area, the CCA. How's that done?
Right. The CCA, the land that can actually be farmed and irrigated, they first identify and mark it out physically on the ground.
Okay.
Then that same area is outlined on the topographical maps. This is super important because the size of the CCA tells them how much water the system needs to deliver the demand. Discharge calculation relies on it.
Got it. So that wraps up the first big stage, project selection and identification. What's next on the list?
Next up is the pre-feasibility study. This comes after that initial field visit. Its goal is basically to double-check those early assessments of the intake area, the canal route, the command area.
Sort of a reality check.
Yeah, pretty much. To get a more solid idea if the project looks viable before committing to the really detailed, expensive studies.
And what happens during this pre-feasibility stage? What activities?
It involves a bit more surveying, but still tentative. They'd survey the headworks, canal, and command area again, maybe using tape measures, handheld GPS for better accuracy, perhaps some basic mapping software.
So refining the initial picture.
Exactly. The output is usually tentative maps and survey data, plus a report. That report summarizes findings and crucially recommends whether or not to proceed to the next, much more detailed phase.
Which brings us to stage 3. The detailed feasibility study. This sounds like where the real nitty-gritty starts.
That's right. If the pre-feasibility looks good, you move into detail feasibility. The survey we have mentions the specs here are often based on official standards, like the Irrigation Department's norms from 2072 in Nepal.
Okay.
And a key first step here is establishing control points.
Control points, what are they and why are they so important?
They're basically super precise reference markers on the ground. Known horizontal position, known elevation. Think of them as anchors for all the surveying that follows.
Well, everything's measured relative to these points.
Exactly. It ensures accuracy across the whole project area. The survey mentions using techniques like traverse, measuring angles and distances between points, or GNSS, which is like super accurate GPS, and it stresses careful calculation and error adjustment.
Are there specific standards for these points, like how accurate or how many?
Oh, yes. Quite specific. For benchmarks, the elevation markers, the standard is usually every half kilometer in hills,
Right.
every kilometer in flatter areas like the Terai Plains, and also at permanent structures. They need to be in stable spots, unlikely to move. They're set using a closed traverse a loop survey that helps check errors, aiming for an accuracy of 1 in 10,000 horizontally, using a local map projection like UTM. For vertical accuracy elevation, it's even tighter. A closed level loop with 1 in 5,000 accuracy tied to a known vertical datum or baseline.
Wow, that is precise. So, framework established. What gets surveyed in detail next?
The focus shifts to the detail survey of the headworks area. This involves a whole battery of specialized surveys.
Like what?
Topographical surveys, mapping the land shape. Longitudinal sections along the river, cross-sections across it. Geological surveys looking at rock and soil. Hydrological surveys checking the water, including its quality. River morphology, how the river channel behaves. Sedimentation. Even environmental surveys for impact assessments.
A very thorough look at the source area. Any specific requirements for how they do these surveys?
Definitely. The site plan, for instance, needs to cover the river's full width, plus at least 100 meters back on each bank, or 5 meters above the highest flood level, whichever is more. Profiles along the river and cross-sections across it need to be taken for a kilometer upstream and downstream from the intake, at intervals of 100 meters or less. These must show riverbed level, the high flood mark, bank tops. And again, using the right tools and methods for quality control is emphasized.
It sounds like they're building a really detailed 3D picture of that whole intake zone.
That's exactly the goal. To develop a digital surface model, a DTM, using CAD-compatible software. This model gets built from all those cross-sections, spot height measurements, and break lines showing sharp changes like ridges, drains, roads, riverbanks.
And the detail level.
High enough to generate contour lines showing equal elevation. The required interval depends on the terrain. 0.25 meters in flat areas, 0.5 meters on gentle slopes, 1 meter on steeper slopes or in hills. The aim is detailed maps of the headworks at about a 1 to 1,000 scale.
Okay, headworks covered. What about the detailed study of canal alignment?
Right. Now focusing on the canal's path. This starts with preparing a strip map, a long, narrow map of the proposed route. Geotechnical investigation is key here, drilling along the center line to find bedrock depth.
Checking foundations again?
Yep. Permanent benchmarks are set along this route, too. Then, detailed contour maps are made for a strip usually 100 meters wide, 50 meters either side of the center line. This mapping might use older methods like plane tables or tachyometers or modern total stations.
Capturing everything in that corridor.
Everything. All natural features, streams, woods, and man-made ones, roads, buildings, fences within that 100-meter strip are recorded.
The survey mentioned newer tech is used now, too.
It did, yeah. For smaller areas, drones or UAVs can do these strip surveys efficiently. For really large projects, LiDAR from aircraft gives incredibly detailed data.
Regardless of the tech.
Regardless, they collect details where the canal crosses roads or railways needed for designing culverts or bridges. If it crosses a river, very detailed surveys are done there too, 500 meters upstream and downstream. They also check the water table and take soil samples regularly along the route, maybe every 200 meters.
And how is this data presented?
The profile along the canal is usually drawn with different horizontal and vertical scales, maybe 1.100000 horizontal, 1.100 vertical, to exaggerate the slope for clarity. And cross-sections across the alignment are taken wherever needed based on the terrain, not just at fixed intervals, based on actual survey data, not guesswork.
Got it. And the last detailed survey area, the command area. What's the focus there?
The command area, remember, is the farmland that will get the water, usually lower than the canal. This survey happens after the canal alignment is studied. It looks at the total area, gross command area, GCA, and the part suitable for farming, cultivable command area, CCA. It maps out the network of smaller distribution canals needed within the CCA and notes important features like existing drains.
What specific types of surveys happen here?
Several kinds. Agricultural surveys, what's grown now, farming practices, soil surveys classifying soil types. Infiltration rate tests how fast does water soak into this specific soil. That's crucial for water management. And environmental surveys, again, for this area.
Okay, so after all that incredibly detailed surveying, headworks, canal, command area, what's the next logical step towards actually building this thing?
Right. Now you move into detailed design and estimate. This is where engineers take all that survey data and actually design the structures, the intake, the canal, crossings, everything on paper, or rather in software nowadays.
Using the maps and profiles.
Exactly. Experienced irrigation engineers review everything, draw the final canal alignment, finalize the intake design, aiming for something technically sound and cost-effective.
What are the big design considerations here?
Stability of location is paramount. Minimizing earthwork costs, cutting and filling, is always a goal. Maintaining the correct canal gradient is crucial for flow. And, of course, ensuring the structures are strong and will last. This is highly technical work done by irrigation experts. And importantly, this final design gets locked in before the next step.
Which is putting stakes in the ground. The final location survey.
Precisely. Now you take the finalized design from the drawings and mark it out on the actual land. The final location survey involves accurately fixing the canal alignment on the ground, respecting the designed gradient.
How do they mark it?
Usually with pegs or stakes along the center line of the final route. Then pillars or markers are put in to show the planned width of the canal on both sides. Same process for any secondary canals. And critically, during this, they record all the info needed for land acquisition and compensation.
All the details for who owns what piece of land needed.
Exactly.
And this whole massive effort culminates in the final step, the final survey report. What gets pulled together in that document?
This is the big one. The comprehensive report covering everything. It includes an introduction, the project justification, why it's needed, why this alignment, details for land compensation, detailed cost estimates for everything, headworks, canals, structures.
A full budget?
A full budget, yeah. Plus the complete technical specifications. A benefit-cost analysis to show it's economically viable, recommendations for implementation, and, of course, all the final maps and engineering drawings, profiles, cross-sections, everything produced along the way.
Now, beyond those main three components, headworks, canal, command area, the survey mentioned other structures sometimes needed. Does they get surveyed too?
Yes, absolutely. The survey points out that irrigation systems often include other major structures, and their specific locations also need detailed surveys.
Like what, for example?
Examples given are siphons pipes to carry water under obstacles like roads or rivers, settling basins to let silt drop out of the water before it enters the canals, and escapes, basically safety valves, channels to release excess water safely if needed.
And the survey method for these?
For these major structures, the survey stresses using direct survey methods. No interpolation or estimating between points. You need precise data right at that specific location.
Got it. Finally, the survey briefly touched on how projects are classified in Nepal based on size. Can you recap that?
Sure. It's pretty straightforward. Medium-scale projects are defined by the command area size, up to 1,000 hectares in the hills and up to 5,000 hectares in the Terai Plains.
And large scale.
Large scale are just anything bigger than that, so over 1,000 hectares in the hills or over 5,000 hectares in the Terai. The source also had some objective and subjective questions listed, but those seem like assessment tools for understanding the process and not part of the project classification itself.
So there you have it. I mean, it's a truly meticulous multi-stage process, isn't it? Just to get water where crops need it, amazing blend of fieldwork, high-tech measurement, careful planning.
Absolutely. Every single one of those stages, from the initial idea or request right through to that final detailed report, is critical. It has to be done right to ensure the whole project works successfully. Really highlights the engineering effort behind something many of us probably just take for granted.
It really does make you think.
Yeah.
You know, considering all this incredibly detailed planning just to bring water to fields, what do you think are the biggest future challenges for irrigation going forward, especially with, climate change, environmental shifts, growing populations?
That's a huge question.
Definitely something to ponder. Thanks for walking us through this deep dive today.
My pleasure. It's a fascinating topic.